For this chapter, we're going to look at solutions in general. We're going to start with a discussion on electrically conducting solutions. Then we're going to look at reactions in solutions, and we'll consider acid-base reactions and the formation of solid precipitates, and a lot of details when it comes to solutions. So the first few slides I'm going to show you will give you some detailed information as to how to think about molecules and ions in solution. An important experiment is just this simple one here, to look at whether if a solution can conduct electricity or not, and it tells you something about it being ionic if it's the case. So blow it up a little bit here. The discussion starts then with some water and some sodium chloride. Table salt is added to it. It's hooked up to this conductivity apparatus where you have two strips of metal. They could be copper, oftentimes they're copper. These would be the electrodes. When hooked to a battery, then one electrode is polarized negative, the other one is polarized positive. And if you put a light bulb in the circuit, it'll light up when the electrons are moving and there's a current. So the reaction for sodium chloride, which takes place in this system, you start with sodium chloride. You want to put S for solid there. Put it in water. You can put water just over the arrow since it doesn't react. And this will break up into sodium plus AQ, tells you water molecules are surrounding this sodium ion, and then chloride also is negative and water molecules are surrounding it. So AQ stands for aqueous. All right, so then the next part of this is that the chloride swims up to the electrode and gives up an electron to become chlorine. And chlorine doesn't exist as just the atom itself. Instead, it wants to make a diatomic molecule. So it does so with two chlorides to form Cl2, and then you have two electrons. And chlorine is a gas. I have to put it on the top here. Should be putting it right next to it. It's a gas. This is AQ, that's aqueous. And so you would see bubbles associated with the chlorine gas. Right now, the electrons are picked up. So this would be like the positive electrode. The chloride swims up to it and gives its two electrons to this system. So the electrons are going to flow through the light bulb and come through, and then they're going to end up over here. And then the positive sodium will swim up to the negatively charged electrode and grab the electrons that are kind of sitting at the surface here. And the next part of this is that the next part of it is that the sodium grabs, you gotta, if two are given off, you gotta need two, even though it's only one electron per sodium ion, to form two sodium atoms. And we just put solid here. You could think that maybe they would precipitate out to the bottom, but in fact there's a secondary reaction that takes place where sodium will react with water to form sodium hydroxide, but that's not the issue here. The issue here is that the electrons given up by the anion, the negatively charged ion, are picked up by the cation, which is a positively charged ion, and in the process some work's been done, which means that the light bulb has lit. All right, so that's the idea for the electrolysis. And now we want to just talk about solutions and what happens. So you can learn a lot just by doing these electrolysis experiments. And you have different substances. One is sucrose, C12H22O11. Put that in solution, and your light bulb does not light up. and so that's referred to as a non-electrolyte. Electrolyte solutions conduct electricity, and this one does not. Acetic acid, you make maybe like a 1 molar solution, 1 mole per liter of water solution. Take some of that, put it in the beaker, and what you see here is just the light bulb is kind of dimly lit, but it is lit. So you can say, okay, it's an electrolyte, but it's a weak electrolyte relative to a strong electrolyte. If you had the same concentration of 1 mole per liter with sodium chloride instead, you'll see that many more electrons are flowing through the wires to light the light bulb brightly. And that's an indication of a strong electrolyte. Now, in solution, what happens is, seen in these little pictures here, you have the sucrose molecule, which is pretty big. You have carbons are black. You can't see them very well, but they're hidden in there. And then there's oxygens, which are red, and hydrogens, which are white. So these blobs here are the sucrose molecules, and nothing happens to them. You put them in water, they just dissolve. You got water molecules that surround these covalently bonded molecules of sucrose, and that's pretty much what happens. In the case of acetic acid, you've got some dissociation associated with it being a weak electrolyte. And let's see. This part right here would be the part of the acetic acid that gave up its hydrogen, which has a positive charge, and so the acetate part, remainder part, is negative and left over. Some of them are not dissociated, but here's an example where they are associated and dissociated, and water molecules tend to aggregate. So water, I'll show it to you on the next slide. It's got kind of a positive and a negative end to it, partial positive, partial negative. So the oxygen here would be slightly negative, and if this were correct, you'd expect that oxygen to be pointing to the positive part of it. Okay, and then sodium chloride, you get 100% dissociation of sodium chloride. The green chlorides are here, and you can see the hydrogen end of the water molecules are facing or attracted to, not bound, but kind of like a electrostatic interaction, an ion dipole interaction, which we'll study later. And then here's the positive end, and you got like a negative end of the oxygen in water being attracted to that. So, kind of outline this for you here. Here's a picture of water on the top, so oxygen, hydrogen, hydrogen, and there's just like a slight polarity. Each one of these covalent bonds here, you know how to draw that. So oxygen, hydrogen, hydrogen. Get some electrons over here. And so you get just kind of a pull in this direction. The oxygen pulls the electrons in the bonds towards itself, means it's a little bit electronegative. And that's how you end up with these partial negative and partial positive parts of water. The bonds are still covalent, but a little bit polar. So water itself is a non-electrolyte, and that means it does not conduct electricity. That's if it's pure water. HCl, you got a great big chlorine here and a little hydrogen. Here's the water, and what happens here is the hydrogen from, get rid of that thing, okay. So the hydrogen from the HCl comes over to the water. So the HCl completely breaks up. The hydrogen separates as a H+. Sometimes we indicate that with an H+ over the arrow. It just means that that's the form in which the hydrogen is moving away from the HCl. And so you end up with the H+ added to the H2O here, and then you end up with this species called hydronium. So this is hydrogen that is surrounded by one of these water molecules, basically. And then chloride becomes negative. So you end up with an ionic situation. It's a strong acid. Strong acids dissociate 100%. And it's a strong electrolyte as well because you have 100% hydronium and 100% chloride. The next one is the acetic acid, which you saw on the last slide. This one, it's hard to find a good depiction of what I'm trying to say here. So this is the structure of acetic acid. You get some electrons here, but don't worry about those. And you can see this kind of organic group here, that's CH3, that's called methyl. This part of the molecule makes it an acid. This is called the carboxylic acid group. In organic molecules, you can attach anything with carbon to the carboxylic acid group, and then therefore it's an organic acid. So this could be methyl, ethyl, propyl, depending on how many carbons, and you can have all kinds of things attached. So it is an acid, not the type that you think about with HCl, but this hydrogen right here is the acidic hydrogen, and this is kind of a 3D model there. This is the ball and stick model as opposed to the space filling model depiction. I actually like the ball and stick better myself because you can see it better. So this is the acidic hydrogen. It breaks away and comes over to the water, and then it ends up over here in the form of the H3O plus the hydronium. What's left is the acetate, so this part gets removed, and this all stays the same. The difference here is that the electrons that are in the bond here stay behind. So hydrogen comes off without its electron. That's why it's got a positive charge. So the H plus comes over and grabs that water and becomes H3O plus. And then that extra electron in the bond that wasn't removed with the hydrogen ends up over here, and that's why this thing has a negative charge. Okay, so the probability for that happening is much lower than some of these simple acids like HCl. So you get, it's referred to as a weak acid. We're going to study those next semester, but all you need to know right now is that you don't get too much dissociation. So 1% dissociation is typical for acetic acid. So you get that dimly lit light bulb. All right, the next one here is sucrose. This is the ball and stick model, and this is the space filling model. So you can see in the ball and stick model that sucrose has got these rings. It's actually got two of them. This one's a little bit harder to see. And then they're connected. And these bonds are covalent. There's no acid group. There's no COOH on sucrose. So no part of this molecule has a tendency to break off into water. And so it's 0% dissociation, non-electrolyte. And you didn't see any effect then with the light bulb. All right, sodium chloride. I gave you the reaction and how that goes on the first slide there. It does undergo 100% dissociation, and it is a strong electrolyte. This picture from your book's kind of nice. I like it. This is the solid that you take some solid sodium chloride and throw it in water. And before it breaks up, you can see this array, this very organized set of, I'm drawing squares here, but it's 3 dimensions. So that's a cube. And you can talk about the cube and what's inside that cube as the unit cell. So we talk about the unit cell when we talk about solids like this. In any event, when it goes into water, they just start popping off. And they're held together as positive negative ions. It's an electrostatic interaction with the ionic compound, and then they come off as ions as well. So there's thermodynamically there's not a lot going on there, except that the interactions break up here, and then you get new interactions because water molecules will solvate the ions. So the sodium plus is going to be attracted to that negative end of the water. You see the reds are closer to the positive. And then the white hydrogens, the more positive end of water, ends up being attracted to the negative chloride. Chloride is larger than sodium. We're going to talk about the diameter and radii of ions after we learn a little bit about quantum mechanics and things like that. So a couple chapters down the road. 100% this thing breaks up and you get a nice bright light there. Okay, so bases, sodium hydroxide here versus ammonia. Sodium hydroxide is a strong base, but don't worry about that. We're talking about it being a strong electrolyte. I don't have the electrodes here, but if you did this, well, they'd be both in here. If you did the experiment, you'd see it was 100%. For the same concentration, it would be the same intensity of the glowing light. And you got sodium positive hydroxide. That's a polyatomic ion. The OH stays together as a negatively charged unit. Here's the positive sodium. Here is the hydroxide. And then if it's hard to find figures for this, but next thing you want to think about is how the water molecules solvate around. They form solvation shells, by the way, or solvation spheres. And you can have 2 and 3 and 4 spheres or shells around each one of these ions, by the way. All right, so that's what happens there. The polyatomic ions stay intact. Then here's an example of a weak base. This is very different. This is NH3. So NH3. And water has that hydrogen here. That hydrogen comes off in the form of H plus and comes right over here and makes a bond, and you end up with NH4 plus. So put brackets around the whole thing, and that would be positively charged. And when the water breaks up into H plus and OH minus, here's the OH minus. It's got the negative on it, and that's what's left over. Okay, so this is an example of a weak base. It's not an ionic compound. It's covalent. And it is a weak electrolyte, which is what you want to focus on here. And it's similar to acetic acid. It's about 1% dissociation as well. All right, so you learn a lot about the structure of molecules from these real simple experiments. All right, I just told you all that. Okay, the next topic we're going to talk about here is the patterns of chemical reactions. For the most part, the ones in your book are given here. There are a few in your book. This is for Cal Lutheran students during the COVID-19 pandemic semester where we're online, and the oxidation reduction reactions are not going to be taught this semester. We're trying to save a little bit of time, but you're going to get them next semester instead. So you'll see them in your book, but you can read about them, but we'll go back to those next semester. All right, so in water, in solutions, you can consider different types of chemical reactions here. The first type is combination, then you have decomposition. Combustion is very common, and we can talk about single displacement. There's also a double displacement, which is a few slides down from this set. So combination reactions, they're simple. A plus B forms C. They just combine. There's no other D. There's nothing else. And you want to make sure they're balanced. And here's an example where sodium solid combines with chlorine to form sodium plus and chloride minus, the ionic solid here. Decomposition, you start with D and it forms E and F. So you just break it up. And you need 2 water molecules to end up with H2 and O2 as products. So just one thing breaks up into 2 or more parts. Reacts, and not just a breakup, it's actually a reaction that takes place. The third one is combustion, and notice that this has got carbon in it, so this is an organic molecule. You can take any organic molecule and react it with oxygen. So this is when we say combustion. This molecule is combusted. This is butane here, like in your butane lighter. This molecule is combusted by oxygen. This molecule is burned in the presence of oxygen, or you could say it's oxidized. This molecule is oxidized by oxygen. So in any event, you just want to be aware of those different terms. And in this case, it's always the case that CO2 and water are the products. So organic molecule plus oxygen forms CO2 and water. That's what you want to remember. And then, of course, you want to write down that butane is a liquid in your lighter until you vaporize it. Oxygen's a gas. CO2 is a gas. Water is a liquid. And notice that the phases are present in all of these parts of these different reactions. It's important to have the formulas correct, the phases, and the coefficients. All right, the last one is called displacement reaction. This is a single one. And the formula here, a little bit tricky. You have a solid, usually it's a metal. You're going to throw it into a solution, which would be like a metal ion plus an anion, metal cation, anion. And then this A has the ability to bump the B out. And the A becomes a cation, and the B becomes the neutral metal. So you get B plus AX. Example here is copper. When you add that to a solution of silver nitrate, the copper has the ability to kind of bump out that silver and become silver solid and copper nitrate. So we're going to use the activity series there to predict those products. So let's back up for a second. Trying to see. Yeah, okay. I want to introduce what's called the net ionic equation. And I suppose we could do it right here. Let's do this first, and then we'll predict what's going to happen. So with these single displacement reactions, there's kind of the essence of what's going on. And if you take the silver nitrate, for example, and break it up into its ions, so this one would be called the molecular equation, the whole thing written out. The next step is called the ionic equation. It gives you just more insight into the situation. So you got copper solid stays the same, and then break up your silver nitrate because it's aqueous. You know that it's because it's an ionic compound. It should, in principle anyway. Most times, not all times, but most times they break up. And you have like 100% association. So you have silver, and then the polyatomic ion stays intact. It does not break up into nitrogen or oxygen. And then you have aqueous for that. And then it forms the silver solid plus copper. You're going to break this one up. AQ plus nitrate. AQ. So this is what's going on when you put it in water. When you write it as the molecular equation, but what it really looks like is the ionic, given by the ionic equation. All right, so a little bit more insight here. You can find what are called the spectator ions. The spectator ions are the same on both sides. So you've got a nitrate here and a nitrate here. The nitrate is the spectator ion for this system. The nitrates are present in the solution, but they're not involved in the reaction. So we can leave them in. They're there in solution, or we can cross them out and come up with a net ionic equation. Net, that's an N. Net ionic equation. I don't like that. Hold on. net ionic equation, and then it would just be what you got left over. So copper solid reacts with silver ion to form silver solid. Solids are neutral, right? So silver neutral plus copper ion. So copper neutral plus silver ion forms silver neutral plus copper ion. And yeah, the last two here on the right, you could flip those if you could write it as copper solid plus silver plus forms copper plus silver solid. That would be fine. So what's going on here? There's a transfer of an electron. We're not really studying the charge and the oxidation numbers this semester to keep it a little bit shorter. But basically there's an electron that comes from copper over to the silver and makes it neutral. And when this one loses the electron, it becomes plus. So there's a transfer of an electron in this process. Now, this is the general pattern here. You have A plus B plus, B positive, forms B plus A positive. And it could be, plus 2 charges, minus 3, whatever, but that's the general idea. Now, you can use what's called the activity series to predict whether this reaction actually occurs. So when you put copper in with silver nitride, will you get the single displacement reaction or not? We've got copper and silver to consider. We see here it ends up as +1. So in other words, the electron will move from the copper to the silver plus so that the more stable copper plus ion will form. So that's the activity series, and you would have that available to you when you're taking a quiz or a test or doing your sapling homework. Okay, so I think that's next, yeah. And that's what we're looking at here. Okay, so this is a table where you can think about these elements that are, their position in this table. And the ones that are higher in the table have a greater tendency when combined with one lower in the table for the one higher in the table to be oxidized, which means in the plus state. So this means in the plus state. All right, so if you go back here, so where's copper? Right there. And silver is here. So if you mix them together, copper wants to be copper +1, that's the activity series which will help you predict it. So iron and copper, let's see, here's copper, and iron is here, okay? So iron versus copper, iron is the one that will end up in the plus state. So look again. We've got, where's the zinc? Zinc and magnesium right here. So magnesium would rather be in the plus state. More we can look at here. And the first one is iron and copper. The second one is zinc and magnesium. So if you start out with iron neutral here and mix it with copper +2, then you're going to get iron 2. So the product here, in other words, the reaction will occur. You're going to end up with FeCl2. That's a Q there. Plus copper solid. All right, and the next one then, you have zinc and magnesium. Hold on. There we go. Zinc and magnesium. And that is the situation on the left here. This is +2. Each one of those chlorides is -1, right? So magnesium is in the +2 state, or it's in the plus state. And so there's no reaction that's going to take place. No reaction that's going to take place. In other words, will it become magnesium solid plus zinc 2+? And the answer is no, because magnesium's higher than the So for this, the first one you can write out just like I showed you in the last slide, get the net ionic equation. For this second one, let's go ahead and look at what the net ionic equation would be for it. And you can write the ionic equation first. If you want to figure out what cancels and what doesn't, it's really important that when you break them up, you do it correctly. So you want to have the count on the chlorides correct. Each chloride has got a negative charge. It's really important that you put your charges in. Students tend to be lazy about it. They just write Cl. Oh, everybody knows what I mean. No, you have to write the charges out. You have to be very specific about everything here. So since there's no reaction, you're going to get zinc solid plus magnesium 2+ aqueous. And then the two chlorides. Okay, so then when you look at it all together, the magnesium 2+ cancels, the zinc cancels, the two chlorides. See how the form is exactly the same there, the two chlorides cancel. So there's nothing left over, there's no reaction. And of course the ions didn't go away, they're there in solution, the zinc solid is still there, but there's no reaction. So you can just picture it as zinc sitting in the bottom of the beaker and magnesium and chloride ions moving about in solution. That's actually what's happening with that system. All right, so you've got two more reactions. The first one is called the double displacement reaction, formation of precipitate, and the second one is the acid-base reaction. In either case, you've got molecules, something like this, AB aqueous plus CD aqueous. And in a double displacement, what you want to do, think about exchanging partners, hands maybe. Sometimes people say exchanging hands. So the positive A will combine with the negative D that way, and then the positive C will combine with the negative B. You're always going to write the positive first. The cation is listed first, and then the anion. So you would expect here for this to be AD aqueous plus CB aqueous. Okay, it's not always aqueous. Actually, I probably should not even have put them in. So let me just erase the inner part right there. You don't know. One of them will be aqueous, but the other one will not necessarily be aqueous. In the case of the formation of the precipitate, you're going to have solid for one of them, and then it would be aqueous for the other. And it doesn't matter which one. But solid be the formation of the precipitate. So that's the first type, formation of the precipitate. Those are also called metathesis reactions. where the precipitates are formed. These are the insoluble compounds. So you mix A and D together, and that combination is very strong. The ions are bound strongly, and instead of breaking up and becoming solvated by water molecules, they'd rather stay together, which means it's a solid. And that insoluble solid will precipitate. It will fall out to the bottom of the beaker, and you'll see that solid on the bottom. All right. In the other case, the acid-base reactions, that will be different. There are some examples where you get solids, but in general, you don't. You would have both being aqueous. Many examples where they're both aqueous. Okay, so for the acid-base reactions. So we're going to look at details of both types, A and B. So we've just gone through 4 types of reactions on the last couple of slides. Now here's 2 more on the list. We're leaving out oxidation reduction. But before we start, you know, when you have the possibility of forming that solid precipitate in your beaker, in your solution, the issue is how much of that solid material will dissolve. Will it completely dissolve, or a little tiny bit of it will dissolve, or none of it? And when we say something has a certain solubility, is the solubility high? Is it low? Will it be soluble? What we're referring to is an actual concentration. So it's the total amount, the total number of grams or moles of solute that will dissolve in a given quantity of solvent to form a solution. For the example of silver chloride, this is considered to be an insoluble compound. And let me make a note about that. Insoluble versus soluble. This is terminology from the good old days when I was your age and studying chemistry in college. And nowadays we use a different term for it, slightly soluble. Okay, so people tend to still use that word insoluble when you're talking about the precipitate sitting in the bottom of the beaker. But slightly soluble gives you a little bit more information. And if you look at what I've written here, the solubility of silver chloride, which is the total amount of the solute that will dissolve, in this case it's 100 grams of water, is 5.2 times 10 to the minus 4 grams. So and notice the temperature is given here. The only reason why is because if you heat it up, more of the solute molecule, silver chloride, will dissolve. So remember, with solutions, you have the solute. Let's back up for a second here. Solute is the thing that's going to be dissolved. The solvent would be water, or sometimes you have organic liquids that's going to be doing the dissolving, and then together they form the solution. Okay, so think about this again. The concentration, or the amount that will dissolve, the solubility of silver chloride is 5.2 times 10 to the minus 4 grams in 100 grams or 100 milliliters of water. Now, most of us think about molarity, or moles of silver chloride per liter. If you do a conversion, you're going to get 3.6 times 10 to the minus 7 moles instead of, so in other words, if you go from grams to moles here, and 100 grams to a liter. So this is not very much right here, 10 to the minus 7. Tiny bit is dissolved, but most of it is sitting in the bottom of the beaker as a solid. And that, you'd say that's an insoluble compound. Or that's the term slightly soluble is telling you that a little bit is dissolved, and that's true. 10 to the minus 7 moles of it are dissolved in an entire liter, which is not very much. All right, so your solubility rules here. This is from an older book, so we're using the term soluble and insoluble. I think most books, even today, still use those terms for the table. And you can come up with some rules here. You have ions from group 1, lithium, sodium, potassium, or ammonium. They're all +1. and those are soluble when they're combined with any anion. So ammonium chloride, potassium chloride, sodium chloride, like that. No exceptions. Group 1 plus ammonium plus 1 ions are soluble when they're in the form of a salt and then put into solution. Same things with acetates and nitrates. Your book, I think, doesn't show you this one, and it's important to know this one, actually. So all nitrate solutions, all acetate solutions are soluble. Now, we were just looking at silver chloride here. So the chloride, bromide, and iodide set here, most of them are soluble. And here are the exceptions. Silver chloride is insoluble, will form the precipitate just like mercurous chloride, lead 2 chloride, silver bromide. So it's the chlorides, the bromides, and the iodides. For silver, mercury, and lead. Then the sulfates here, most of them are soluble, and here are the exceptions. Calcium sulfate. This one's got some dissolving, but not enough to call it soluble. And barium and strontium. Barium sulfate, if you've ever done any imaging of your intestines, usually you will do, you'll drink a solution of barium sulfate, since it forms a precipitate as it moves through your intestinal system. The x-rays can pick up that solid. You get images of the solid, which could, indicate some blockages, things like that in the intestines. Some kind of need for surgery, perhaps. You do that before surgery. All right, and then the line underneath, most of them are insoluble. Most of the carbonates, phosphates, sulfides, and hydroxides are insoluble, with the exception of group 1A carbonates and ammonium carbonate. So group 1A and ammonium, all of those are going to be soluble, right? Same thing here with the phosphates, group 1A and ammonium. Group 1A and ammonium. So these guys, the carbonates, phosphates, and sulfides are going to be soluble. With the hydroxides, group 1A hydroxide, so that's the same. They don't have the ammonium in here, but they should put it in because it is true. Ammonium hydroxide is going to be soluble. But then they add calcium, strontium, and barium hydroxides to the list of compounds that are going to be soluble. All right, so even if it were a normal semester and you we're just going to walk in and take a written test, I would probably give you this table for the solubility rules. It's a lot to memorize. Some of them are easy, acetates, and if you want to put a system together where everything's soluble, it'd be real easy to use these guys, right? All right, so let's play around with this a little bit. Is sodium sulfide soluble? So sulfide is in the lower half of that table, S2 minus. And most sulfides are insoluble except for group 1A. So this one is going to be soluble. Is it soluble? Yes. And so you would write Na2SAQ. So AQ tells you that the sodium and the sulfide, this is sodium plus, this is S2 minus, the molecule will break up into ions, and the ions will be solvated by water. That's what it means for it to be soluble. It's an aqueous solution. All right, lead bromide, if you look up the bromides, most of them are soluble. You go back to the last slide. Lead bromide was listed as one that is insoluble. You say no. So this one would be PbBr2 solid. You don't break it up. You leave it as the solid. Iron 3 hydroxide or ferric hydroxide. Most hydroxides are insoluble with the exception of group 1A and ammonium and so on. So this one is not going to be soluble either. No, it is not soluble. Yes, it is insoluble. So be careful when you're just saying yes or no how the question's written. And We don't break this up because it exists as a solid. So we just put solid like that. All right, so now we want to do the double exchange. We don't have to do all of these, but let's go ahead and look at the first one. So if you combine lead and chloride and sodium and nitrate, sodium and nitrate. So sodium salts are going to be soluble, nitrate salts are soluble. So this part right here is going to be soluble, but lead chloride is not. You have to go back and look at the table for this. So do the double exchange, write it out first, see what makes sense. So you got lead, and lead's got a 2+ charge. You're going to need 2 chlorides. You got to get the formulas right. And the other one is going to be sodium nitrate. So we know for sure that this one is going to be soluble. Sodium will be soluble and nitrate will be soluble. And you'd want to go to your table, and if you did, you would find that lead chloride is a solid. All right, and then the last thing is to make sure it's balanced. To get the 2 chlorides on the right, for lead chloride, you're going to need a 2 right here. That means you're going to need 2 sodiums, and you got 2 nitrates already. Okay, so if we went ahead and wrote the net ionic equation for this one, usually you write them vertically. I'm writing horizontally because I'm writing on this slide here. If it's a solid, you're going to keep it together, and then it's going to break up as 2 sodium plus aqueous. You got to know all the details when you're writing this out. Plus 2 nitrates. The nitrate is a polyatomic ion that stays together, does not break up into nitrogen and oxygen. And that would be the product there. That would be the system. So, I guess I probably do have to write this down below. I want to show you how to get to the net ionic equation here, so bear with me. I'm going to write this again. So you're going to get, you want to write, this is your molecular equation right here. Okay, so let's write that out first. So you did the double exchange, you figured out what the new formulas are going to be, you figured out which one is soluble and which one is not. Then you want to write the ionic equation. And this is, if it's aqueous, you can break it up. So it's going to be lead 2 plus aqueous plus 2 nitrate aqueous plus 2 sodium aqueous plus 2 chloride aqueous forms lead, chloride solid. You do not break that up when you write the ionic equation. And then you're going to write 2 sodium plus 2 nitrate like that. All right. Then you want your ionic net rather. So you're going to take those spectators, and they should be the same on both sides. That's how you know they're the spectators. And then you have the net ionic equation, lead 2 plus aqueous plus 2 chloride forms lead chloride solid. So this is the essence of the reaction. That's the net ionic equation. You could put lead nitrate. You could, here, you have lead nitrate. You could put lead, I don't know, you could put lead sulfate. You could put lead iodide, things like that. In other words, it doesn't matter what this one is. And you could mix something with lead, and then you could have sodium chloride, potassium chloride, lithium chloride, like that, so that the counter ion, as long as it's soluble, doesn't matter. So this is the essence of the reaction. Maybe you don't have lead nitrate on the shelf, but you can pull some other lead 2+ compound that's aqueous, and you can still carry out the chemical reaction. All right, so then you got barium chloride and sodium sulfate. In this case, when you do the double exchange, you're going to get barium sulfate solid plus 2 sodium chloride aqueous, and that's a precipitate. The next one, you're going to do your double exchange and get silver chloride solid plus sodium nitrate aqueous. So you can write that. That's a reaction that precedes. If you get a solid precipitate, right, then you can say, okay, I've got a chemical reaction. You can pour off the solution, which contains sodium chloride, for example. You can isolate the solid barium sulfate. It's a way to make barium sulfate using these precipitate reactions. All right, the last one, you've got zinc chloride. And this one turns out to be aqueous. And then you got barium nitrate. And that one is aqueous as well. So there's no reaction on number 4. All right, you can work out the details, the net ionic equation for those. Now I want to talk about acid-base reactions. That's the other double exchange type of reaction. Here's pictures of 2 acids, vinegar and lemon, and ammonia, that's CnH3, and bicarbonate, which is baking soda. Sodium hydrogen carbonate, also called sodium bicarbonate, that's the common name. And they're both basic. All right, you mix them together, you get a reaction. So here we have some examples for acid-base reaction. It's a double exchange again. So you could look at H and OH combining, and sodium and bromide. Double exchange. So you could get NaBr aqueous plus H2O liquid, or you could write aqueous there for that. And the pattern here is acid plus base forms salt plus water. That's the pattern in the acid-base reaction. It's an acid because it's got the H given on the left-hand side here. And it's got the hydroxide for the base. And those things are going to break up and potentially react. Okay, so let's see. Let's go ahead and do an ionic equation. Actually, let's do an ionic equation for the next one. They're all the same. The second one is going to be, let's see. This is, you have 2 hydroxides. This is different. You got 2 hydroxides and 1 H+. Actually, in light of that fact, let's go back to this one here and do the net ionic equation for it. All right, so you got H plus Br minus plus sodium plus hydroxide polyatomic ion forms sodium bromide is aqueous, so it'll be sodium plus bromide. And water, which is covalent, you do not break up. Liquid. All right, then you want to cancel out your spectator ions. This becomes a very interesting result. And the interesting result is the net ionic equation. And all the acid-base reactions are like this, more or less. There's some, with the weak bases, it's a little different, but other than that, we're good. So the essence, we would say the motivating force in an acid-base reaction is the formation of molecular water. The covalent bonds are very stable, and once formed, they're not going to break up. Okay. So let's take a moment and look at some of the other ones here. So the second one is HClO4, that is perchloric acid, plus calcium hydroxide forms. You're going to do the double exchange. So it's going to be calcium, that's a 2+, perchlorate's got a -1. Need 2 of those. That'll be aqueous. Plus, and then you've got 2 hydroxides and 1 H+. So you're going to have to, and you've already got 2 perchlorates in the system now. So you need a 2 there for sure. Okay, and then you'll have 2 waters being made, 2 H+ and 2 OH-. Right, if you write out the ionic equation, let's do a different color for that. Let's do green. So it's going to be 2H+ aqueous plus 2 perchlorate aqueous plus calcium 2+ aqueous plus 2 hydroxide aqueous forms calcium 2+ aqueous plus 2 perchlorate aqueous plus, you're not going to break up the water, 2 waters in the liquid. Okay, so now we're going to block out the spectator ions. Perchlorate have to be exactly the same on both sides. And then the net ionic equation, we got 2H+ aqueous plus 2 hydroxide aqueous forms 2 waters. Cancel out the 2's. H+ plus hydroxide forms H2O. So the same thing's going on in this acid-base reaction. H+ from the acid, hydroxide from the base, combined to form water. And let's see, the last one is acetic acid. Let's get a different color for that so we can track it. Acetic acid plus sodium hydroxide. So this one be down here. And it's HCH3CO2 plus NaOH. And I'll give you the answer and then I'm going to draw a picture. So this hydrogen here comes off the acid in the form of H+ and combines with the OH-. So you're going to end up with acetate, CH3CO2- plus water. Liquid, this is aqueous, like that. All right, so if you got rid of the acetate on both sides and the sodium on both sides, you would end up with H plus OH minus forms H2O. But I wanted to show you the structure on the acetic acid to show you this unique system. This is organic molecule. So if you remember, for acetic acid, it's got this methyl group on it. Here's carbon. That's acetic acid. Put it with some sodium plus some hydroxide here. What will happen? So on the acid group here, the carboxylic acid group, the H plus breaks away in the form, the hydrogen breaks away in the form of the H plus, and the two electrons here, one of them that comes from the acetate, the other one from the hydrogen, both of them end up over here. So that's why you end up with a negative charge. So then you end up with acetate. With the methyl group on it. So the hydrogen is gone, and the extra electron remains. So that's negative. And then this hydrogen comes off as H plus and connects with the hydroxide. So you get water, liquid water here. Okay, so then this, you remember acetic acid is a weak acid, so you get, if it were in water, it would be 1% dissociation, but in the case of it being with a strong base, the hydroxide will drive this reaction 100% to the right. And you've got H plus OH minus forming H2O for that one as well. So this is the nature of the acid-base reactions. A lot of detail there, which you need to be able to write out and be real comfortable with. Phases, everything. All right, so here's a list of some strong acids, HCl, HBr, HI. These are the 6 strong acids that are found in nature. There's only 6. Perchloric acid, nitric acid, and sulfuric acid. The hydroxides, group 1 metal ions plus hydroxide, group 2 metal ions plus hydroxide, and then in group 13 it's aluminum, for example. So you can get sodium hydroxide, calcium hydroxide, or aluminum hydroxide. Those are some examples of strong bases, 100% dissociation. Don't worry about those. That comes up next semester with some detail. All right, let's look at some balancing here. And these, similar to the balancing equations that we looked at earlier. In this case, you can see you've got this sulfate. If you make this with a coefficient of 1, the only form of the sulfur on both sides is sulfate. So since this molecule has 3 sulfates, you're going to have 3 sulfates on the left-hand side. So you can just put the 3 in there. Okay, that's useful. Also, if you have 2 irons, you're going to have 2 here. And the rest of it should be easy. How many hydroxides are there? Now, you could have kind of approached this a little bit differently, but we're here, so I'll just point it out to you. There are a total of 6 H pluses here, a total of 6 hydroxides here. So H plus OH minus forms water, and you can make 6 of them like that. Now, if you don't like that, you can just sit there and try and balance sulfur and oxygen and hydrogen. But these are some clues. If you know the nature of these acid-base reactions, you can balance them pretty quickly just by thinking about how the H's and the OH minus combine. The next one, you've got cesium phosphate. I would make that one the most complicated. Let's put a 1 there. That's going to give a 3 over here, and a 1 for the phosphate there. Then let's see, we have 3 hydroxides on the left, 3 H pluses on the left. So you combine them, you're going to get 3 waters. So you can go through this and check it and count each atom and make sure all the charges balanced and everything, but that's how it will work out for that system. Okay, so just some easy ways for balanced acid-based reactions. Monoprotic acids have one. The H plus that I've been referring to is also called the proton. And if you think about what a hydrogen is, it has 1 proton, 1 electron, and 0 neutrons. If the hydrogen breaks away from the molecule and leaves its electron behind, the only thing left is the proton. So when the H plus breaks away, it is in fact a proton. Okay, so monoprotic means 1 proton per molecule, for example, HCl. Diprotic, you've got 2 H's per molecule in sulfuric acid. Triprotic acid, you know it's an acid because the H's are written on the left. Triprotic acid, you have 3 hydrogens in 1 acid molecule there. All right, so I think I need to take a break here. I'll come back and work on this video a little bit more. All right, back again. You have to take a break. This is just so much material all at once. Take a break, practice it, work examples, come back to it, whatever you need to do. All right, so I'm going to go through this as well. This is some detail about the different types of acids. So the monoprotic acid we've already been looking at, and you got HCl as a monoprotic acid, 1 proton there. We've been looking at it reacting with hydroxide, but what happens when it's in water? And the answer is the proton, which is the H plus, leaves the HCl and hooks up with the water to form hydronium. So you've got here, there should be an arrow there, gonna form chloride. Tired. Plus hydronium. Like that. All right, so if you wrote out the ionic equation, you'd have H plus chloride, leave water associated because it's covalent. Excuse me, and you got chloride. And hydronium is the same. You don't break it up, it stays together like that. So the spectator ions here are the chloride. The net ionic equation is H plus H2O forms H3O plus. This is another important reaction in acid-base chemistry. We spent a lot of time on that next semester. The diprotic acid, excuse me, H2SO4, let's do that one in blue. So you have H2SO4 aqueous plus water. Actually, in this case, it's going to be 2 waters. And you're going to form sulfate, 2 minus, plus 2 hydronium ions. So one at a time, you've got the H coming over to the water. H plus coming over the water. So this is kind of the overall reaction, but if you want to look at the stepwise process, that gives you more insight into it. So this would be the overall reaction. Here we want to write out the stepwise process. So start with H2SO4 aqueous plus water. And stepwise means it's going to be one proton at a time coming over here. So you're going to end up with hydrogen sulfate or bisulfate ion, because you remove one proton, and one hydronium ion, like that. And then in the next step, we take this hydrogen sulfate and we put it as a second step in the reaction. Hydrogen sulfate will react with another water molecule to form another hydronium. So HSO4 minus plus a second water molecule will form sulfate. So the proton again, the second proton gets removed and put over here with water. And you're going to have a second hydronium ion generated. Now, if you add these up, your hydrogen sulfate is like the spectator. It's not included in the overall, but it's still there, and it's actually very important. It's more concentrated than the sulfate itself is. And also with sulfuric acid, the first... Never mind, I won't even talk about that. Wait till next semester. So add them up. You're going to have H2SO4 plus 2 waters form sulfate plus 2 hydronium ions. And that's what I already had given you up here. So when you add up the 2 steps in this mechanism, you get the overall process there. Okay, and that's good enough. As far as the net ionic equation goes, I'm not going to ask for that. It's for these, you want to just look at the different steps. Now you should be able to do the phosphoric acid yourself. So with the phosphoric acid, you've got 3 protons. Oops. And here they are, H3PO4. So with that one, you can write out the steps, but the first step will be phosphoric acid gives up 1 hydrogen to form dihydrogen phosphate. This gives up another proton to form hydrogen phosphate. And then the next step is to form a phosphate, like that. So stepwise, so there's, instead of having 2 steps in the mechanism, you've got 3. You should try this one on your own. And if you want to look it up, the hydrolysis of phosphoric acid, you'll see the steps, or we can go over them together during a office hour situation online. All right, getting towards the end there, we're going to talk about acid-base titrations and some of the chemistry, some of the math associated with concentrations and so on. So start out by talking about molarity. It's a unit of concentration. We've used it a couple of times already, but it's the number of moles of solute per liter of solution. So molarity has the symbol M. M molarity is going to be moles of solute divided by liter of solution. And let's see. When we say we have, for example, so if I told you your concentration is 2.5 m, for example, you would say 2.5 molar. So the unit here is spoken as the word molar. The molarity is 2.5 molar. I'm just trying to give you the wording here. So the molarity, or the concentration, is 2.5 molar. That's how you would say it. And if you were going to write it, you'd say the molarity is 2.5 m for molar. You'll see what I mean as we go ahead. All right, here's how to do it. Let's say we wanted a solution of copper sulfate here. So we're going to weigh out 39.9 grams of it, which corresponds to 0.25 moles. So you're going to use molar mass. If you want 0.25 moles, you're going to have to weigh out 39.9 grams of this beautiful blue solid. You're going to take your solid, which you have weighed out here, put it in this volumetric flask, and you can't really see it. I don't think you can see it even if I blow it up. But when they come from the factory, there'll be a line that has been etched in it to give you the exact volume. In this case, I think this is a 250 milliliter flask. So the convention here is to put the solid in, mix it together, and then add water until you fill it up to the mark. And it's going to look like this. So your water, your solution, has this capillary effect, and the bottom of what's called the meniscus is going to hit the line that's etched by the factory for precise work. All right, so it shows you pouring water in there, and you want to swirl it around a couple of times before you start adding more and more and more of it till you get it up the neck. Oh, there it is down at the bottom. It's a little bit, the line was a little bit further down than I indicated. But usually there's a little bit of heat given off in the process as well, so you want to wait for that heat to dissipate because that tends to increase the volume a little bit. That's a quantitative analysis technique. And then finally you're going to fill it to the mark and put the little cover on it. They don't show that. And then you tilt it upside down, back and forth until it's all mixed together here. And let's see what it says here. Put copper sulfate solute into the 250 milliliter volumetric flask, add water, and swirl to dissolve. Add water until the solution just reaches the calibration mark on the neck of the flask, and swirl to mix. So what would the concentration be here? You're going to have 0.25 moles of copper sulfate solute. And it's divided, you want to put it in liters here, so 250 milliliters is 0.250 liters, and certainly you have a solution of it. So this is going to be a 1.00 molar copper sulfate solution. Okay, all right, that's how you do it. If you want 1 molar, you take that flask and you weigh out 39.95 grams. All right, what's the molarity of a solution that's 2 grams sodium hydroxide in 500 milliliters of solution? So for this one, get my calculator here. So for part A here, you have 2 grams sodium hydroxide. 23 plus 16 plus 1, it says we're going to use 40 grams per mole. Sodium hydroxide, 23 plus 16 plus 1, so it's going to be 40 moles per gram, grams per mole. And this will give us moles of sodium hydroxide. And then we're going to divide it by the volume. You got 500 milliliters, so that's 0.5 liters. Let's calculate that. 2 divided by 40, and then divided by 0.5. So this is going to be a 0.1 molar sodium hydroxide solution. All right, part B, this is a little different. How many grams of sodium sulfate are needed to make 250 mils of 0.1 molar? If you know that molarity is moles over volume of solution. Molarity is moles divided by volume. Solve for moles. It's molarity times volume. So this is a very useful form of the equation. The number of moles is molarity times volume. So you know you want a certain molarity. In this 1.1, you know you're going to need a certain volume of it. Multiply those together to get moles, and then use molar mass to get sodium sulfate. And let's see, we have the moles for this case are 0.10 molar times 0.250 liters. So that's going to be 0.0250 moles of sodium sulfate. I don't know what the Molar Mass of that one is. I can look it up in periodic table, or I can Google it. Molar Mass sodium sulfate, 142.04. So that's molarity times, sorry, that's moles. So mass then is going to be equal to, so mass will be equal to 142.04 grams per mole. You're going to multiply that times 0.025 moles here, and the mass will be equal to, that 142.04 times 0.025. So this will be 3.551 grams, or 3.55, but I would weigh one extra sig fig for rounding purposes later, of Na2SO4. So it'll be 3.55 grams you're going to weigh out. You're going to put it in a 500, nope, you're going to put it in a 250 milliliter flask, shake it up, and you have a 0.1 molar solution of sodium sulfate. Okay, so then the next topic is titration, acid-base titration. And here you have a very interesting process. You can take your acid like HCl and put it in a flask with water. You can take some sodium hydroxide and put it in your burette. Your burette is a glass tube that's very precisely calibrated by the factory, so you can measure to either the 10th place or the 100th place of volume. You measure your initial volume and then your final volume by difference. That's the amount that you let out, and that would be the volume of your sodium hydroxide solution, for example. And in this case, you have a neutralization process where you start with acid, the H plus down here in the flask, and you're going to drop in the hydroxide, and it neutralizes to form water here. And it will keep doing that until all the H pluses have been consumed. As soon as you have the exact same number of hydroxides and H pluses in the flask, the system is completely neutral. That would be referred to as the end point of the reaction, or the equivalence point. And if you add an indicator, the indicator in this case is most probably phenolphthalein. And let me write that down. It's just a couple of drops of a solution with a molecule that changes its color based on the acid form or the protonated form and the base form or the deprotonated form. This particular one that turns pink is called phenolphthalein, phthalene, phenolphthalein. It has the property that it's clear in acid solution or neutral solution, and it is pink in basic solution or base. So what happens here is that you keep adding in. You can see as soon as it completely neutralizes the H pluses, which in the beginning it's a very localized place in the solution where it's getting neutral, and then you got one more little hydroxide ion added, and then the system is basic, and then it turns pink like this. But as soon as you start seeing it starting in certain parts of the solution, then you want to swirl it. You want to swirl the flask and move it around until all this kind of dissipates. And then finally, when it turns pink and stays pink, then you know that all of your H plus has been neutralized by the hydroxide. And here you got water plus some excess OH minus. So right at that point, if you go any further, if you keep eating hydroxide, it's going to get darker and darker and darker. Actually, the way this is depicted is as it's completely neutral, it's pink. So I think when I said here clear in neutral, that probably want to look that up, but I think I got that wrong. It's in neutral, it's going to be pink as well, according to this figure. All right, so the goal of these experiments is to get that endpoint to be as pale pink as possible. And if you mess up, you have to repeat the whole thing until you get it with that exact condition. If it's too dark pink, nobody likes that. You toss it and start all over again. All right, so why do we care about this? Because there's a relationship here. You've got the moles of H plus being equal to the moles of hydroxide at the equivalence point. And maybe you know the concentration here and can use molarity times volume as moles. That'll be equal to the moles here that have been neutralized. So the moles that you let out are equal to the moles that were just neutralized. And if you know the volume of the solution and the moles, you can go back and get your molarity. And oftentimes you don't know the molarity precisely, and so you do these experiments to get the exact concentration of your unknown acid, something like that. Well, variations on that, of course. All right, here's another one. In my opinion, this is a little bit too pink. Toss it, start all over again. But here's, see how you got the swirl there? This is just the region of the solution that's neutralized. But when you mix it all back together, it'll go clear. That's kind of a fun thing to see in the lab. All right, monoprotic monohydroxy. It's a simple relationship here that moles of H plus equals moles of OH minus at the equivalence point. Moles is molarity times volume, so molarity of the acid times volume of the acid will be equal to molarity of the base times volume of the base. This is a really nice, simple, handy equation. And it works if you've got monoprotic hydrogen, monohydroxy, sodium hydroxide. One hydroxyl group per molecule. All right, so let's read it again. What's the molarity of 25 mils HCl? So you know the volume of your HCl in the flask, but you don't know the concentration. And you've titrated it with 18.01 mils of 0.1 molar sodium hydroxide. So actually, let me grab my notes here on this stuff. I've got all this worked out. Find it. Okay. That's the one. Nope. 25 mils and 18.01. Where'd that one go? I can't find it. Doesn't matter. So for the acid, the molarity is the unknown, and you've got 25 milliliters of the acid solution. When it was neutralized, it was done so with 0.100 molar sodium hydroxide. And we can keep these in milliliters as long as it's milliliters on both sides, or you could convert to liters. That would be 0.01801 liters and 0.025 liters on the left. But here, you can easily get the molarity of your acid. And this would be 0.1 times 18.01 divided by 25. So this will be 0.072, how many sig figs here? 4? 0.4. Molar. Molarity of the acid, 0.07204. Alright, then the next one here, diprotic monohydroxy base. So this one is for sulfuric acid, and my notes are missing on this stuff. So for this one, you're not going to use M1V1 is equal to M2V2, and that is because you've got a diprotic acid. That equation only works for monoprotic monohydroxy. So instead, you just have to treat it like a regular stoichiometry problem. Let's write the balanced chemical equation here. You got H2SO4, leaving off the phases here, plus 2 sodium hydroxides. I got 2 H pluses, so I'm going to need 2 OH minuses. That's why I put the 2 in there. So this is going to form sodium sulfate aqueous plus 2 H2O. 2 H2O. All right, so take your molarity times volume for the sulfuric acid and put that here. Then it'll be a 2-to-1 relationship for how much sodium hydroxide is needed, and that will be in volume, I guess. Then you're going to combine your information with molarity to figure out, I'm sorry, moles, sorry, wrong. Let's just do it instead of giving me the whole outline anyway. Okay, so let's see here. You can say 0.175 molar H2SO4 multiplied times volume. Now here, I would go ahead, molarity times volume is moles. Molarity is moles per liter. I would go ahead and put that in liters. It's a good habit, which later you'll use all the time. So this is going to be, because the unit for molarity here is in fact mole per liter, you can see that the liters are going to cancel. So if we stop here, we have moles of sulfuric acid. The next step is to use a 2-to-1 ratio. 2 moles of sodium hydroxide are needed to neutralize 1 mole of H2SO4. And now we have moles of sodium hydroxide. Well, let's go ahead and calculate that. So 0.175 times 0.035 times, whoops, not divide, times 2, syntax error, times 2, messed up. Let me do it again. 0.175 times 0.035 times 2. Okay, needed to neutralize the sulfuric acid. Now you've got the question, how many milliliters of a 0.25 molar solution of sodium hydroxide have to be reacted? Well, you know how many moles you need. What does that correspond to in terms of volume? So if you say molarity times volume is moles, and the question is how many milliliters, so what's the volume? This will be equal to moles divided by molarity. The moles that you need to neutralize in this 2-to-1 reaction divided by the molarity of sodium hydroxide, 0.250 moles per liter, moles divided by liters, and so let's divide that by 0.25. So this will be 0.0490 liters. Oops. Sodium hydroxide, which would go back now. You go to milliliters, 49.0 milliliters sodium hydroxide needed. He's barking at the kids in the pool. All right, that's how you do that one. If it's a 2-to-1 reaction, you may not use molarity of the acid times volume of the acid is molarity of the base times volume of the base. Instead, you're going to use your coefficients here. You're going to use that to calculate moles of hydroxide, and then you're going to work your way backwards here to get volume from molarity times volume is moles. All right, moles per liter will be now. This one is titration of an unknown solid acid. This is very typical for the lab. They'll give you an unknown. Let's see if we can keep them quiet there. Okay, so picture this. You've got a flask and you put some solid in there. You weigh out 2.635 grams of it. It's an unknown. Your TA gives it to you, and you got to figure out its molar mass. So you put it in a container with 25 milliliters of water, and you're going to titrate it with, here's your burette. It's a tall burette. So it takes 21.38 milliliters of sodium hydroxide. This is the acid here. All right, my dog is barking. I keep stopping and deleting parts of this video. He's barking at the pool, people in the pool out there. All right, anyway, so we got, where were we? 25 mils of the unknown acid. We don't know the molarity of it. We have sodium hydroxide in the burette. We know that it's 1 molar and it takes 21.38 milliliters to neutralize the unknown solid acid. It doesn't say here, but it is a monoprotic acid. Let's keep it simple here. All right, so I think we're ready. We can use for sodium hydroxide 1 molar. Molarity times volume is moles, right? So 0.02138 liters of it needed to neutralize the acid. So that's 0.02138 moles of sodium hydroxide needed. And the next step is the question is, what is the molar mass for this one? So capital M is the symbol for molar mass, but since molarity is the same, why don't we go ahead and do MM for molar mass, something like that, or M with a subscript M, sometimes you see that. And molar mass is going to be mass divided by moles, right? Grams per mole, those are the units of periodic table, I just remember it that way. So the mass is going to be, this is of the acid now, 2.635 grams of the unknown acid, and the number of moles corresponds to that amount of substance, grams per mole. So you've got here 2.635 divided by 0.2138. And that is, something wrong with that. Let me try it again. 2.635 divided by 0.2138. 12. It's impossible for it to be 12. Oh, I see. Yeah, so 0.0, that one's wrong right there. So that'll make it 123 grams per mole. A little distracted here by the dog. All right, that'll do it. That's 3. Oh, you need one more sig fig, so 123.2. 123.2 grams per mole. Now, there's lots of organic molecules that are solids, these white solids. Oftentimes they're given in the lab as an unknown, and a molar mass of 123 is completely expected and normal for an acid. Something like benzoic acid, for example, might have a mass about that value. All right, that would be how you would treat your unknown. Molarity times volume of the base in the burette, which is put into the flask, and then you've got your weighed out mass. Calculate molar mass from that. All right, the last topic is dilution. And remember that molarity times volume is moles. In this case, you're going to have a concentrated solution. You're going to take part of that and put it in a new flask, add some water to get a dilute solution. So the concentrated solution is called the stock solution, and when you dilute it, it's the diluted solution. I think I got a nice figure for that here. Okay, this is from the Cal Lutheran book, which is Brown and LeMay. All right, so you've got a flask. In this case, it's a 250. Sorry, my dog again. Okay, I get a little distracted. You have a 250 milliliter volumetric flask, and it's filled with the stock solution. So this is the stock over here. This is the concentrated one. You're going to take 25 milliliters of the concentrated stock solution. You're going to take it up with your pipette, and then you're going to bring it up and put it into the empty flask. And when you do that, here it is. So you've taken out 25 milliliters and of the stock and put it into the new flask. Then you're going to add some water and now shake it up, and then you have your new solution. So this is your diluted solution here. All right, so let's look at what it was. I think this is a simple one. So you're going to use M1V1, that would be for the stock, is equal to M2V2 for the diluted solution. And why can you do that? You're saying you've taken a certain number of moles of the stock solution. You put that same number of moles in the new solution, in the new flask, and added water. The number of moles is the same, it's just the volume of water that makes it concentrated versus dilute. All right, so let's see. You've got a 1 molar solution of stock, and you're taking 25 mils. You could write down 0.025 liters. Either way is fine. And you want to, let's say you don't know what the molarity is going to be when you put it in the new 250 milliliter flask. Okay, so you're going to solve for M2, and it's going to be 0.1. So solve for 0.2 here, and that'll be a 0.1 molar solution. So you've gone from a 1 molar concentrated to a 0.1 molar dilute solution using this technique. So it's just a way to make up some more dilute solutions. And let's see, what else about this? Yeah, I think that's good. All right, one calculation here. This is the last slide, and the number's already done for us. How many milliliters of a 0.1 of a 1.25 molar concentrated stock solution are needed to prepare 500 mils of a 0.25 molar solution of sodium hydroxide. So this is typical. You know what you want to make, 500 mils of a 0.2 molar hydroxide solution, and this is what you got. You got this concentrated solution. That's maybe from the stockroom. So the stockroom gives you the 1.25 molar, and you've got to do this calculation. This is for the concentrated 1.25 molar times what volume do you need to put into the new flask, which is 500 mils, in order to make 0.02 molar. So then solve for volume there. And the way this is written in milliliters as well. So if you have milliliters on both sides, that works out, or you have liters on both sides, that works out fine. That would be 0.008 liters needed. But you can't mix it up. You got to have one or the other. So solve for V1 there. That's the amount of stock solution needed, 8 milliliters of 1.25 molar. Put it in the 500 milliliter flask, and you're going to get 0.02 molar. All right, we are done with this whole chapter. Hopefully it took you a couple of days to get through all this, because it's pretty quick, and you definitely are exposed to a lot of new things here, and you want to take it slow and practice and, you know, work examples and think about things. But the good thing is you can scroll back and forth, and you can stop and look at your notes and your book to help you out there. Well, have a good one.